Imagine I've just handed you a small glass vial. It's maybe no bigger than a shot glass, and it's filled with this incredibly fine, sparkling white dust. It weighs almost nothing in your hand.
Okay, so I'm holding a little vial of powder.
Yeah.
Got it. Looks pretty ordinary.
It does. But here's the mind-bending part. Get this. If you could somehow take every single one of those microscopic crystals in that pinch of dust and, unfold them.
Unfold them? What do you mean?
I mean, flatten out every internal tunnel, every single chamber, every little cavity inside each crystal. If you could lay all that internal surface area out flat, you'd be standing on a surface larger than the entire floor space of the Empire State Building.
Wait, hang on. Seriously.
Maybe even twice the size.
That breaks every rule of physics I thought I knew. How can something that fits in my palm have, hundreds of thousands of square feet of space inside it? That sounds like science fiction.
It totally does. And that impossible scale is exactly why we're talking about it. This isn't just chemistry. It's architecture that completely defies common sense. It's so counterintuitive that when the Nobel Committee awarded the prize for this, they had to reach for fantasy to explain it.
What did they say?
They literally compared it to the tardies from Doctor Who and Hermione Granger's infinitely expandable handbag from Harry Potter.
Wow. Okay, so they're basically saying it's magic. That's a huge statement from the Nobel Committee.
And that's exactly what we're diving into today. This invisible, unimaginable container, these tiny crystals holding impossibly vast amounts of empty space, are called metal organic frameworks, or MOFs. And their design, the incredible achievement of building something like this with atomic-level precision, is why Richard Robson, Susumu Kitagawa, and Omar Yaghi were just awarded the 2025 Nobel Prize in Chemistry.
So our mission today is to unpack the how. How on earth did they build this molecular TARDIS? And more importantly, why is turning a simple powder into a gigantic internal sponge? Why is that the key to, clean energy and the future of the planet?
We have the blueprints right here. And when you talk about the sheer scale, we have to underscore this. When Omar Yaghi first published his big one, MOF5, it didn't just break the record for porosity, it shat in it. It had a surface area of about 2,900 square meters for a single gram.
Okay, stop. 2,900 square meters from 1 gram. Let's put that in perspective. A paperclip weighs about a gram. So you're saying an amount of this powder that weighs less than a paperclip has enough internal surface area to cover 6 professional basketball courts.
Exactly. And they didn't even stop there. Later designs pushed it way further. MOF 210 clocked in at a colossal 10,400 square meters per gram. That achievement alone is why this is so foundational.
Okay, that is true molecular mastery. So let's start at the beginning. What was the roadblock? What was the problem that made this kind of thing seem like magic in the first place?
To really appreciate how elegant MOFs are, we have to look back at material science before them. For almost a century, the villain of the story wasn't a chemical. It was the method itself. It was serendipity.
Happy accidents, chemistry by just hoping for the best.
Precisely. For 100 years, if you wanted a new, solid material, especially one with a useful internal structure like, say, zeolites, which are these porous minerals used as filters.
Right, like in water filters or cat litter.
You basically had two choices. You found it in nature, or you just mixed a bunch of chemicals together, heated them up, crossed your fingers, and hoped the atoms would magically line up in some new, useful way.
So if I needed, for example, a molecular cage that only lets water molecules through but stops, say, salt ions, I couldn't design it. I just had to throw ingredients into a chemical pressure cooker and see what popped out.
You had no blueprints, no guarantee of what you get, absolutely no control. You could build small, simple molecules all day long, but building vast, crystalline 3D solids, it was basically impossible to do it on purpose.
That sounds like being able to make a single perfect brick, but having no idea how to build a skyscraper that doesn't immediately collapse.
That's a perfect analogy. And it wasn't just about building any solid, it had to be a durable one. It needed to withstand heat, pressure, all the stresses of industrial use. But the materials that are strong enough for that, like metal oxides, are incredibly hard to shape with any kind of precision.
So they needed the strength of, concrete and steel, but with the detailed, customizable architecture of, a microchip. And that combination was the impossible dream.
But there were hints it was possible. The idea of a porous framework wasn't totally new. There were these things called coordination polymers, which were kind of like early, messy prototypes of MOFs.
Yeah.
But they were found, not designed.
And you mentioned Prussian blue. That's a paint color, right? From the 1700s?
Yes, exactly. A deep blue pigment. discovered completely by accident. But what's so wild is what chemists found when they finally figured out its crystal structure
Yeah.
in 1977.
And what did they find?
They found that Prussian blue is actually this beautiful, ordered, three-dimensional cubic lattice. It's a framework of iron ions connected by cyanide groups. And the key thing was, this framework had empty spaces, cavities, that were filled with water molecules.
No way. So for 300 years, we'd been using a material that proved you could build a precise crystalline cage with empty space inside. But we had no idea how we did it. It was like a masterpiece meal with no recipe.
Exactly. It showed the potential, but it didn't give us the rules. And that brings us back to the central challenge that doomed all the early attempts at this stability.
The House of Cards problem.
Precisely.
Right.
Let's say you actually managed to make one of these early porous structures. To make it useful, you have to activate it. You have to clean out all the solvent molecules, the water, that are clogging up the pores from the creation process.
So you have to, what, heat it up or put it in a vacuum?
Right. And the moment you did that, the whole thing just collapsed. The bonds holding it together were too weak. Removing the guest molecules inside was like kicking out the support pillars of a cathedral. The whole thing just folded in on itself.
That's a total failure. I mean, if your material can't even survive being dried, it's useless for any real-world application. It needs to survive that and then be used over and over again, thousands of times.
Absolutely. So we needed a new kind of chemistry, something that could give us three things at once: huge internal space, perfect geometric order, and rock-solid stability.
Yeah.
We needed molecular architects.
Okay, so the villain is chaos and fragility. Who are the heroes who bring order to the molecular universe?
Well, this wasn't one single eureka moment. It was more like a decades-long relay race between three incredible minds. We start with Richard Robson, who had the first spark of the idea.
This is the famous story of the wooden models.
The very same. We're in Melbourne, 1974. Robson is a lecturer, and he's got this tedious job of building big wooden models of crystals like table salt for his first-year students.
Like a life-size chemistry set.
Exactly. And as he's drilling holes in these wooden balls for the sticks to go in, he has this incredible insight. He realizes that by drilling the holes at precise, predetermined angles, say 4 holes in a perfect tetrahedron, he was forcing the balls to snap together in only one possible way.
Ah, so the final shape wasn't random. It was being programmed into the pieces themselves.
That was the core idea. He called it directional bonding. If wooden balls could self-assemble based on pre-drilled angles, why couldn't molecules? Why not design molecules with specific shapes that would act like custom Lego pieces and build themselves into a huge, ordered structure?
It's such a simple, elegant idea born from such a mundane task. But it took him a while to actually test it, didn't it?
Oh yeah, over a decade. The chemistry just wasn't there yet. He finally tried it in 1989. His plan was to build a structure that mimicked the open, spacious geometry of a diamond.
Okay, so what were his Lego pieces? What was the chemistry?
He needed 2 things: cornerstones and linkers. For his cornerstones, he used positively charged copper ions, because copper naturally likes to form 4 bonds in a kind of pyramid shape.
So the copper ions were his pre-drilled wooden balls.
Got it. And for the linkers, he used these long, 4-armed organic molecules. At the end of each arm, he put a specific chemical group, a nitrile, that was strongly attracted to the copper.
So the linkers were designed to only snap into the copper cornerstones at the right angles. The chemistry basically does the assembly for you. No glue needed.
And it worked. The combination formed a spacious crystal with these big cavities. It was the world's first rationally designed framework, a massive conceptual victory.
There's always a but. This is where the fragility problem comes back, right?
This is exactly where it comes back. The bonds between the copper and the nitriles, they were directional, but they just weren't very strong. As soon as he tried to remove the solvent from inside those big cavities,
The whole thing collapsed.
the whole thing collapsed. It was like he'd built this perfect, beautiful skeleton, but he'd used thread instead of steel bolts. The architecture was brilliant, but the building materials were too weak.
Okay, so he proved the blueprint works, but it's not a usable material yet. That's a critical failure, but also a huge step forward. So who picks up the baton next?
The next leg of the relay goes to Susumu Kitagawa in Japan in the 1990s. His whole focus was solving that stability problem and actually making these things functional.
He needed to find the molecular steel bolts. How did he do it?
In 1997, he had this huge breakthrough. He was working with cobalt ions and a specific linear linker, and he created a framework with a geometry he called a tongue-and-groove structure.
Like interlocking floorboards.
Exactly like that.
Yeah.
This design provided internal reinforcement. And when he heated the material to drive out the water molecules inside, it didn't collapse. The tongue and groove structure physically held the lattice together.
Ah. So the internal mechanics provided the stability. That's the leap. That's the difference between what Robson did Generation 1 and this new Generation 2.
Absolutely.
Yeah.
And because it was stable, he could finally show what these things could do. He proved it acted like a molecular sponge. He could flow gases like methane and oxygen in and out of the dry structure over and over again.
That's the moment it goes from being a cool chemistry novelty to a functional technology. It can breathe.
It can breathe, it can work. And off the back of this, in 1998, Kitagawa basically laid out the roadmap for the entire future of the field. He defined the generations of these materials.
Okay, walk me through the generations. This seems important.
It is. So Generation 1,
Yeah.
that's Robson's early stuff. Porous but unstable, they collapse. Generation 2, that's Kitagawa's breakthrough. Stable frameworks that can reversibly absorb and release things. The durable molecular sponge.
In Generation 3.
Generation 3 is the really futuristic stuff. He called them soft porous crystals. These are dynamic frameworks that don't just stay open. They can actually change their shape. They can open or close their pores in response to things like pressure or temperature.
A smart, shape-shifting crystal. That's incredible. And Kitagawa's first stable one, the tongue and groove framework, was actually one of these.
It was. He didn't just solve the stability problem for Generation 2. He accidentally built a Generation 3 material and laid the intellectual foundation for the next 2 decades of research.
Okay, so we have the blueprint from Robson and the first stable functional sponge from Kitagawa. Now we need scale, and we need, like, industrial strength permanence. And that's where Omar Yaghi comes in.
This is where Omar Yaghi comes in and provides the foundation for the whole field. First, he's the one who actually coined the term metal organic framework, or MOF. And he established the entire discipline of reticular chemistry.
Reticular chemistry sounds like to form a net, stitching things together. So how did he get that permanence that was still kind of missing? What was his secret sauce?
He found the perfect chemical weld. The key ingredient was his choice of linker. He insisted on using a specific kind called carboxylates. It's a group with a carbon and 2 oxygen atoms, and it carries a negative charge.
And why is that the magic ingredient?
Because it forms incredibly strong multi-point bonds with the metal ions. If Robson's nitrile linkers were like weak plastic rivets, Yaghi's carboxylate linkers were like welding the entire framework together. These bonds were strong enough to survive pretty much anything.
Okay, so he solved the strength problem chemically. But what about the other problem, predictability? How did he make sure the structure came out perfectly every single time?
That's his other stroke of genius.
Yeah.
The idea of secondary building units, or SBUs, he realized that when you mix these strong carboxylate linkers with metal ions, you don't just get one metal atom at each corner. You get these stable, predefined clusters of metal ions.
So instead of using a single atom as his cornerstone, he was using a prefabricated multi-atom piece.
Exactly. And this is so crucial. Early on, people used single, naked metal ions as the nodes. The problem is, a naked ion is geometrically ambiguous. It can form bonds in all sorts of unpredictable ways.
It's like using a Lego brick that might randomly decide to have 4 studs or 6 studs. Your final building is going to be a total mess.
Right. But the SBU approach fixes that. Yaghi would use a specific rigid metal cluster, like the famous zinc-oxygen tetrahedron. This cluster always has 4 connection points pointing at a perfect pyramid. It removes the ambiguity. It forces the structure to build itself correctly.
That's the heart of reticular chemistry, then. You choose standardized, strong components that lock together in a predetermined pattern. It turns chemistry from a random guess into rational engineering.
And the moment he applied this SBU approach, everything changed. In 1999, he built MOF5. It was the first truly stable, permanently porous MOF, and it immediately set the world record for porosity, 2,900 square meters per gram.
And because the method was so rational, he could just keep improving it, right? But they're just using longer linkers, for instance.
That's the beauty of it. His team went from MOF5 to MOF177, which was 4,500 square meters per gram, and then to the mind-boggling MOF210 in 2010, which hit that 10,400 number. This wasn't luck anymore. This was engineering with atomic precision.
Okay, so let's put it all together. A MOF is a hyperporous material made of metal clusters, the SBUs, connected by rigid organic linkers. And up to 90% of the whole thing can just be empty space.
Exactly. And it's that SBU concept that really separated it from older porous materials, like zeolites.
Right, because with a zeolite, you're kind of stuck with the structure nature gives you. You can't just decide to make the pores bigger.
But with MOFs, you can. That's the ultimate advantage. Tunability. It's like a molecular construction set with interchangeable parts. You can engineer the final product for a specific job.
So what are the main things they can tune?
Well, there are three big ones. First, pore size and shape. You want a bigger pore. You just use a longer linker molecule. It's like adding an extender bar between the cornerstones. The cavity expands by a predictable amount.
Okay, that makes sense. What's the second?
Topology. That's the overall architecture. You can change the entire 3D geometry just by swapping out the SBU. If you replace a 4-connected cornerstone with a 6-connected one, you instantly switch the whole structure from a diamond-like pattern to a cubic one.
And the third must be functionality, like what the inside of the pores actually do.
Exactly. Functionality. You can choose a specific metal for the SBU to make it, say, catalytic or magnetic. Or you can add little chemical hooks to the linkers, something like an abamine group, that specifically grabs onto, say, a CO2 molecule. You can line the walls of your sponge with molecular Velcro.
And this is where computers become so important, right? Because if the design is rational, you can model it first.
Absolutely. Before MOFs, you had to make the material and then measure its properties. It was trial and error. But with reticular chemistry, you can model thousands of different combinations on a supercomputer before you ever step into the lab.
So you can predict the pore size, the stability, even how much gas it will hold.
Yes. Teams like Laura Gagliardi's can computationally design a material for a specific task. It's the ultimate realization of rational design. It completely changed the game.
And this principle, this reticular chemistry, it goes beyond just metals and organics, right?
Yeah.
What about COFs?
Good question. Yaghi extended the same idea to create covalent organic frameworks, or COFs. Same principle of stitching building blocks together with strong directional bonds, but with no metal at all. It's an all-organic structure.
Why would you want to do that? Aren't the metal clusters the key?
Well, covalent bonds are some of the strongest in chemistry, so COFs are incredibly robust, and because they're all organic, they're extremely lightweight. This led to a material called COF 108, which is officially the least dense solid material known to science. It's mostly just nothing.
So the real breakthrough wasn't just MOFs themselves, it was the entire methodology of reticular chemistry, the ability to stitch things together with atomic precision.
That's the Nobel Prize right there, the methodology.
Okay, so we've built the molecular TARDIS. It's stable, it's customizable, it's designed with incredible precision. But can you actually use it? Is this stuff viable on an industrial scale?
That's the billion-dollar question, and the answer is a resounding yes. The key for industry is longevity. These materials are built with such strong bonds that they don't easily degrade. One of the sources mentioned a MOF for water harvesting that maintained its peak performance after 30,000 cycles.
30,000 cycles. That means you can use it every day for decades without replacing it. That's the economic argument right there. So let's talk applications. What are the big ones?
The two biggest are probably solving water scarcity and mitigating climate change. Let's start with water. Yaghi's work on harvesting water from desert air sounds like something out of a sci-fi novel.
Right, even in low humidity. How does that even work?
They use a specially designed MOF 303, that is super hydroscopic. It absolutely loves to suck up water molecules from the air. The device is basically a high-tech humidity sponge. At night, when the humidity is a bit higher, the MOF just passively absorbs water and stores it in its pores.
Okay, so it soaks up the water, but how do you get the water out?
That's the clever part. Because the MOF is so stable, you just need a little bit of low-grade heat to force the water back out. They often mix the MOF powder with a bit of graphite, which gets hot really fast in the sun.
So sunlight heats the graphite, which heats the MOF, and that releases the trapped water as vapor, which you then condense into pure drinking water. That's basically a zero-energy water generator.
Essentially, yes. They've already tested microwave-sized prototypes successfully in the Arizona and Mojave deserts.
And what's the output? Are we talking a few drops or something meaningful?
It's getting meaningful. They can get more than a liter of pure water per day for every kilogram of MOF. The goal is to create household units that can provide 7 to 10 liters a day, enough for a family, and make them water independent. It's a massive humanitarian breakthrough.
Okay, that's huge. What about the other big challenge? Climate change and CO2 capture.
This is where that tunability really shines.
Yeah.
You can design an MOF to specifically target CO2 molecules. They do this by adding those amine groups we talked about to the linkers inside the pores.
The molecular Velcro.
The molecular Velcro. It's like lining the sponge with sticky tape that only grabs CO2 and lets all the other gases from, say, a smokestack like nitrogen pass straight through. The result is a material that can increase its CO2 storage capacity by up to 18 times compared to older materials.
And this is actually being used now.
It is. They're already deploying them in the venting systems of cement plants. There are industrial rigs with big columns packed with MOF pellets. They flow the flue gas through, the MOF grabs the CO2, and clean air comes out the other side.
But then the sponge gets full. What happens then? How do you get the CO2 out and reuse the MOF?
That's the economic magic. Because the MOFs are so stable and the bonds are so specific, you don't need a ton of energy to regenerate them. You just need to change the pressure or pass some low-grade steam through, and the MOF releases a stream of pure captured CO2. Then it's immediately ready for the next cycle.
Incredible. And I assume the same principle works for storing clean energy like hydrogen or natural gas.
Exactly. The big problem with storing gases like methane is you have to compress them to dangerously high pressures to fit enough in a tank.
Yeah.
But if you fill that tank with MOF powder,
The gas molecules cling to all that massive internal surface area.
right, so you can store 3 times the amount of methane in the same tank at a much lower, safer pressure. It makes clean energy infrastructure much more viable. And companies are already scaling up production from grams to tons for these applications.
Okay, so filtration and fuel storage are the present. What about the future? Where else is this technology going?
Well, it's moving into areas you wouldn't expect, like advanced electronics. The big challenge there is that most MOFs are electrical insulators.
Right, so how do you use an insulator in a battery?
You design it to be conductive. But the real advantage isn't just conductivity. It's that the porous structure is a perfect superhighway for ions. In a battery, energy comes from ions moving around. The MOFs ordered tunnels let those ions zip through with incredible speed.
Faster charging batteries.
Potentially much faster charging and longer-lasting batteries, yes.
Yeah.
And even more futuristic is the work in spintronics. That's the idea of storing data using the magnetic spin of an electron, which is way more energy efficient.
To do that, you need a single material that's both magnetic and conductive, which is famously difficult to make.
And MOFs are making it possible. Researchers are building these highly specialized frameworks that are both, which could lead to computer memory that uses a tiny fraction of the energy we use today.
From storing gas to storing data bits, that's some serious versatility.
And maybe the most amazing application is in nanomedicine. They're shrinking MOFs down to nanoparticle size and using them as tiny targeted delivery trucks for chemotherapy drugs.
Okay, walk me through this. How does a MOF deliver a drug?
It's a brilliant multi-step process. First, you load the chemo drug into the MOF's empty pores. The rigid cage protects the toxic drug while it's in the bloodstream. Then you coat the outside of the MOF nanoparticle with molecules that act like a GPS, so it only sticks to cancer cells.
So the delivery truck only goes to the right address.
Only to the tumor. And here's the last part, the release. The environment inside a tumor is more acidic than the rest of the body. The MOF is designed so that its chemical bonds slowly start to dissolve in that acidic environment.
So it only opens the cargo doors and releases the drug once it's inside the tumor.
Exactly. It dumps a high concentration of the drug right where it's needed, which maximizes its effectiveness and dramatically reduces the toxic side effects on the rest of the body. It's incredible application of this architecture.
Wow. It really is the ultimate proof of how this rational design, going from computation to experiment, has changed everything. It's the end of accidental chemistry.
What a journey. I mean, we started with chemists just randomly mixing things and hoping for the best, and we ended with 3 Nobel laureates, Robson, Kitagawa, and Yaghi, who gave us an entirely new way to build.
They didn't just give us a new material, they gave us a new philosophy. Reticular chemistry taught us that we don't have to settle for the materials we find. We can design them with atomic precision to do exactly what we want them to do.
We went from thinking about simple molecules to thinking like molecular architects, building entire 3D worlds on a nanoscale. And the result, the metal organic framework, is this ultimate proof that when you learn how to connect the atomic world with our macroscopic world,
You can solve the biggest challenges we have. Climate, water, energy, health, it's all there.
which leaves us with a final thought for you, the listener. You now know the history of a structure that could genuinely define the 21st century. So if we can reinvent filters, fuel tanks, and even medicine using this technology,
Yeah.
what common material in your daily life is just waiting for its molecular structure to be reinvented?
Yeah, think about the plastic packaging you use, the concrete in the sidewalk, the inefficiency of the phone in your pocket. What common object around you right now is secretly just a poorly designed MOF waiting for an upgrade?
Until next time, keep digging deeper.